Okay. Hi, Christina.
Hi, Christina.
Hey, where's the Midian?
A what?
Hi, Samidian.
Oh, her last name. I was like, okay. Example 1. Find the point or points of discontinuity. So there are 4 types of discontinuity, y'all. What are the 4? 4 types. Whole. Is that a removal?
Yeah.
Yes. Infinite?
Yeah.
Jump?
Oscillator.
Yes. Okay. Everything she said. Now, example 1, ABC, I believe. We have ABC. Okay. It says find the discontinuities. So, how do we start? A. Factor. Very good, Alex. Okay, factor it out. You and your team factor it out. Frankie, once you have the factor, you let me know what the factors are.
X minus 3 and X minus 1.
Okay. Is this reducible? No. So, what do you do now to determine the discontinuities? It's not a whole. What do you do now to find the other kind? Set the factors on the bottom equal to 0. Correct. We're going to take whatever's on the bottom. We're going to take it and set it equal to 0. Okay. Now, I'm going to have 2 x values here that x can never ever be. Can we agree? Well, what do we call these? Old school. Those are called vertical asymptotes. New school.
Infinite discontinuity.
Infinite discontinuity. Okay. Infinite discontinuity at where?
At x equals 3
And
x equals 4.
perfect. Okay. Now, by definition, by formal definition, what's the infinite discontinuity formally defined as based on your video notes? Limits. What?
Where x goes to c from the right side is plus or minus infinity, or it's plus or minus infinity from the left side. Or
Okay. So, as x approaches c from the right or left, right? Would you agree? Right or left? Doesn't matter, does it?
Yes.
Yeah? Okay. It equals to what? Either positive or negative infinity. This is just a definition of vertical asymptote. If you recall from the last, if you flip back your notes, vertical asymptote is the same exact definition. Okay. Could I have multiple vertical asymptotes?
Yes.
Sure. Okay. So that's what it is. B for boy. What type or what kind of discontinuity is this? A whole, okay. I'm gonna write whole and question mark. Whole, question mark. If you're taking an exam, what are your guesses? There are 4 choices, right? What can you eliminate right away?
Wait, no.
Oscillation. Yep, I can totally eliminate that. So right now, a whole. What else? What other one can it? A jump possibility. Okay. Can it be a VA, vertical asymptote, infinite? Can it also be an infinite discontinuity?
no.
No? Okay. I'm going to write that anyway. Okay. I just know it can't be an oscillation, okay? So how do we prove that which one's which? What should we do to prove which one's which? You can graph it out, or
No.
we're going to do both. Or what? Or we're going to graph it out. We're going to graph it out, or we're in calculus now. What do we do in calculus?
Use a calculator.
No. You're not going to have one. What have we been doing for the last 2 weeks? Limits! All right.
Yes.
Okay. We're going to do limits. Okay. Shh. Where is the x location in question? 0. X equals 0 is the problem. Would you agree?
Yeah.
Okay. All right. We are going to find the limits as x approaches 0 from the right, and the limits as x approaches 0 from the left, okay, of this function. So this function is x divided by absolute value of x. And then, now, this is the part that's going to confuse a couple of you because of this. Let me talk to you guys about this. Y equals an absolute value of x. Y equals absolute value of x. Okay? Technically, this is a piecewise. Technically, is a piecewise. Someone tell me why it's a piecewise. Why is it a piecewise?
Because it could be defined as y equals negative x from negative infinity to 0 and then y equals positive x from 0 to infinity.
Okay. What Rando is saying is that, okay, we all know that it's supposed to look like a V, right? No doubt. But, and you can see that whatever x is, y is always positive. Yes or no? Yeah. But would you agree that it's kind of like two lines meeting up at 0? Would you also agree that's true? Yeah, two lines, do they have the same slope? No, they don't have the same slope. On the left-hand side, right? When x is less than 0, what is the slope of that side? Is negative. Can we all agree? Let's pause right there. When x is less than 0 or equal to 0, would you agree that this line has a negative slope? Yeah. When x is greater than 0, that line has what? A positive slope. So technically, an absolute value function can be rewritten as a piecewise. Okay. Now, let's talk about our limits. Back to our limits question. Limit as x approaches 0 from the right-hand limit. Which piece should we use? Which piece should we use? The negative x or the positive x? Positive, because I'm coming this way. Can we agree? Yeah. So that's positive x. So x divided by positive x, which I would have a limit of what? 1. Beautiful. Okay. Now, x approaches 0 from the left. Which piece? Negative x. So top x hasn't changed because that's not an absolute value. What's this limit? Okay. Let's go back and define the whole. What makes a whole? Formal definition of a whole is what?
When the limit as x approaches c of x exists but is not equal to f.
Okay, whole means limit as x approaches 0 of f of x exists, okay, but not equal to f of 0. Is that true? Does the limit at 0 exist?
No.
No, the left and right are not exactly the same at all. Would you guys agree with that?
Yeah.
Okay. So, nope, cross that out. A jump? What's the definition of a jump? When x approaches 0 of f of x, does it exist or not exist? Does not exist? Whole? Read it again. Does it exist?
No. Does not exist.
0. Okay. How about the right or left? How about left and right? Exists, but what?
Not equal to.
Not equal to the other side. Okay. Does it meet this condition?
Yes.
Yes. Okay. So guess what? This is a
Jump.
jump. Jump at x equal to what? 0. Okay. Now, earlier, Randall said, let's graph it out. Yes, I should. Just to confirm our analytical work. Analytical, they're calling that now because we're not in algebra anymore. Okay. So, let's graph it out. So, we don't no longer say, oh, so show me algebraically. They say, show me analytically. Okay. Okay, how do I graph this? 0, 1. Is that true? I don't know. That's what Macy said. 0, negative 1? Okay. Would you agree that 0 doesn't exist?
Yeah.
Okay. Can I pick 1? When x is 1, what's the output?
1.
Great. When x is 100, what's the output?
1.
Great. So it goes like that, right? But can I pick something super close to 0? Like 0.000001. When x is 0.0001, what's going on? It's still
1.
1. I'm going to pause right there. Do we agree that it's still 1? Okay. And then it's going to be 1 until it is at 0. Now, how about the negative side?
How do you know which one is an open circle? Which one is closed?
They both should be what? Open, because x can never ever be 0. All right. When x is negative 0.001. Negative 0.01 on the top, right? Divided by absolute value of that is? A negative on the top divided by a positive value will be negative. Can we agree the bottom is negative? Okay. So check this out graphically. Graphically, can you agree it's the same as your analytical? Yep. Okay. The limit on the left is always negative 1. The limit on the right is always positive 1. When in doubt, you can always graph it out. Okay. C, piecewise, which is kind of similar to our B once it's broken down to pieces. Okay. What is the x value in question? 0. Problem at 0? Question mark? Okay. What kind of question? Okay. What kind of problem? A discontinuity? Obviously, right? What kind of discontinuity? A jump, a hole, a vertical asymptote? Okay.
I'm guessing it's
Now, how do we do this? What do we do to find which type of discontinuity? Analytic, okay? Limit as x approaches 0 from the right. Limit as x approaches 0 from the left. If you're taking the limit as x approaches 0 from the right, what piece, which one of those two pieces should we use? 3x minus 1. You're right. So 3x minus 1. Can I substitute? 3 times 0 minus 1 is? Great. Left-hand limit. Which piece should we use? Negative e to the x. Can I substitute? E to the 0 is? Times negative. Oh my. The limit exists. But so is it no discontinuous at all? Is it continuous then?
Yeah. No.
Wait. The limit exists? Whoa. Okay. Limit as x approaches 0 exists, right?
Yes.
Okay. But not equal to what? F of 0. Because does f of 0 even exist? No. So, what can we conclude? It's a hole. Is it removable or non-removable?
Is it always removable? Is a hole always?
Hole is always removable. Removable hole at x equal to what?
0.
Beautiful.
So when it says find the points of discontinuity, we have to say which type of discontinuity.
There's only one type that's removable, so that's a hole. So if it said, is it a removable?
I mean, like if one of us asked to find the points of discontinuity, we have to say
State the name. All right. Let's go do this one. Can you help me, please? Read the instruction. Olivia, just that first line, Olivia.
Use the function f to find the graph below to answer the question.
Great. Okay. So, is this a piecewise?
Yeah.
How many pieces?
5.
A lot. Look, this one, I'm really kind. I even gave you a graph, right?
Yeah.
The next problem, I might not be that kind. Okay. So, the graph is given to you, as well as a function. A, does f of 1 exist? Kylie. A, does f of 1 exist? Kylie says yeah?
Yes.
Yeah? Paul, Kylie says yes? So do you agree with Kylie? Yes, okay. Frankie, what is f of 1 if Kylie said it exists?
F of 1 would happen to be 1.
Okay, yes. F of 1 is 1. Beautiful. Okay. Miles, B, does the limit as x approaches 1 exists?
Yes.
Miles says yes. Mia, do you agree? Yeah. Okay. You guys are awesome. What is the limit as x approaches 1, Macy? 2. Okay. Part C. Alex. Are they equal? No. Great. D. Here we go. Natalie. Is the function continuous as x equals to 1? Teamwork if you need to. Consult with your team. Talk it out. Verbalize it. Okay, Natalie said the answer is, what's your answer? Is it continuous? Natalie gave me the answer. What's your answer? Yes or no? It's not continuous. Okay. Guys, for a function to be continuous at a value of c, the limit has to equal it. So the limit at 1 has to be the same as its value at 1. Is this true? Is the limit at 1 the same as value at 1? No. And also, look at the graph. Okay. Can you guys see that here? Is it continuous here? No, there's a hole, right? A hole means it's not continuous, even though it has an algebraic value, but that is not the same height. Can you guys agree with that? So that's why it's not continuous. Okay? For it to be continuous, the limit at that particular value has to be the same as its algebraic value. Okay? All right, 3. I'm giving you a piecewise, a better looking piecewise, but you have to graph it out. So go ahead. You and your team, work it out. Graph it out for me. Why? Was it loud? Yeah. Oh, sorry. Oh, sorry. Next time. You should have come back and tell me. Next time I should let you stay. Right? Once you are done graphing, can you consult with your mates? So make sure you guys all have the same exact identical graph. If your graph does not look the same as your mate's, convince that your graph is better. Okay. Frankie, do you have the best graph out of the whole team?
I sure do.
Okay. Okay, give me the points, Frankie.
There's a hole at 2-1.
2-1, perfect.
And then there's a point at
2-2. 2-2, okay.
And just draw points at like 1-2.
1-2.
And then 4-2.
4-2.
And draw like lines from the hole to
Okay.
yeah, like that.
My triplets are just started their softball, and softball kids always chant, right? Why is that? The softball girls chant, and the baseball boys don't chant the songs. Like the songs, they're always like singing, you know? Do you guys agree with what I'm saying? Like softballs are always singing. So funny. What?
Baseball? I thought it was so boring.
Yeah.
I quit after like 2 seasons.
Yeah.
It was so bad.
Maybe you just said
I was always great. That's why I don't play anymore. It would be fair to the other kids.
You're right. You would have just been all that.
I was actually.
All right.
Okay.
Sorry, I asked. Oh my gosh.
You got
Woo!
You're bringing up trauma.
Here we go. I will not ask again.
Well, I always struck out. So like.
Do we have a point of discontinuity?
Yes.
Yes. Where is our point of discontinuity?
2-1.
Discontinuity at x equals to what? X equals to 2. Okay. And just find the point of discontinuity. We found it at x equals 2. Now B says, since we only have one point of, just right there, Christina, on the table is fine. Thank you. Since we only have one, okay. What type of discontinuity is this? Is this removable or non-removable? Removable. Removable. And why did you say it was removable? Well, you should come back to it's a whole, it's removable, right? But what else to back it up? The limit. The limit as x approaches 2 is what, by the way? It's 1, right? It's 1. Which is not the same as what? F of 2. Can we agree with that? Okay, so that's a better support of your removable. Okay. All right, we're going to fill out these properties, and this is the end of our day. Here we go. Properties. Properties of continuous. Okay. Casino, we recorded all just for you.
Wow.
And Bendon. Well, she actually really did ask. Go ahead.
Oh, it's still kind of wet.
If f of x and g of x are continuous at a point, okay, let's call this point x equals to c, then here we go. I'm gonna write out the first few properties first, and then I'll give you an algebra review for the last one. So if two functions are continuous at this particular value c, when you add them, okay, so f plus g is continuous as well. Continuous at x equals to c, okay? So if f is continuous at x equals to 2, g is continuous at the same value at 2, then when you combine those two, when you add those two, they're still going to be continuous at x equals 2. Difference. Guess what? It's also the same, okay? When you subtract f minus g or even g minus f, okay, is continuous at x equals c. No surprise there. I can even multiply and divide, and guess what? It's still going to be continuous. So product f times g, okay, f times g is continuous at x equals c. Quotient f divided by g, given that g can never ever be 0, is continuous at x equals to c. I can even multiply each function by a constant. Let's call it k. Constant. Let's call it k. Okay. I can take k, bless you, times f of x, or k times g of x is continuous at x equals to c, given that k is all real numbers, okay, in a set of all real numbers. Now the last one, I'm going to let you guys finish writing, and let me give you an example. Who remembers composition? Because the last definition is composition. Who remembers composition? Do you remember hearing the word composition?
Yeah.
Yeah, okay.
Decomposing vectors, but I don't remember anything about
This is last year.
Oh, wait.
This is last year.
Is this the one with the weird pause?
The bubble, remember this? F bubble G? Yeah, it's the fog. F bubble G. Okay. Oh, I should have just kept fog. Okay. F of G.
Yeah.
Review. Okay. Okay. Shh. Because the definition of composition, it's a little bit more difficult. It's a little bit difficult to comprehend. So I'm going to give you a review first. I will give you f of x and g of x. Okay. I will give you g of x is x. F of x is square root of x. Someone give me the domain of f of x. Domain of f of x. I can't hear you. 0 to infinity.
Yeah.
Okay. Okay. The domain of f. True or false? Is that right?
Yeah.
Yeah. What is the domain of g of x? Negative infinity to infinity, or aka all reals, right? Let's do fog. Or in this case, I'm going to do. Okay. We're going to do. This is the domain is all reals. Now I'm going to do f of g. Is that okay too? I mean g of f. That's what I meant to say. Goth. Okay. By definition, would you agree that this is true? By definition, is that true? Sure. Okay. So let's talk about that really quickly. So how do I find the answer? What did you do? I plug in the f function into what? The g function, right? Because f is inside. What's your f function? Rad. So what's my final answer? What's your final answer? Just rad x. Okay. Can we agree that's true? What's the domain of this composition? Yeah, it is 0 to infinity. Okay. So we did all the algebraic work. So let's talk about, hey, the domain, which is where it's continuous. Okay? So in the radical, which is f of x function, would you agree that it's continuous from 0 all the way to infinity? This is a line. It's continuous always. So when you compose two functions, can you see that it is continuous only where they both what? Overlap. So these two functions overlap when? From 0 to infinity, where the positive side is, right? So that's kind of the same thing here, except that the language is so confusing. I figured if I give you an algebraic review, it makes more sense, okay? So it's continuous, the same thing. So here's the formal written of it, okay? Okie dokie. If f is continuous at x equals c, and g is, oh, thank you. Thanks, Mia. And g is continuous at f of c. Okay? Oh, I forgot. G is continuous. G is continuous at f of c. Okay? So if f is continuous at x equals c and g is continuous at f of c, then g composed with f, which means is g of f of c, okay, is continuous at x equal to c, meaning the limit as x approaches c of the composition is the same as g of f of c. Okay. So the limit at C is just the same as G of C. So all of those just to say this. And that's concluding our day.